Hey there, welcome back to Calc 2. We're going to continue our work in Chapter 11 on testing series for convergence. The Section 11.4 contains two new tests, and they are called the comparison test. We'll just say CT for short, and the limit comparison test, the LCT for short. So the goals of the lectures are to state those tests. I won't give proofs of them in this video lecture. You can ask me about why they work and give how the proofs work in an office hour or in an online Zoom meeting class. Because my main purpose is to get these things stated, then illustrate how to use them with several examples. All right. So maybe just as a real quick intro, let's just kind of remind ourselves what we're doing. Our fundamental question in life right now is given a series whose terms are called a sub n's, does that series converge or does that series diverge? That's the fundamental question. Do the sequence of partial sums have a limit or not? Yeah, and we have so far 4 tests that we can use to try to answer those questions. None of them are perfect. None of them answer this question about all series, but together they give us kind of a toolbox to think about. The divergence test is something I actually think about first. It's in section 11.2. It's the one where you take the limit of the terms. Yeah, somebody hands you a series and you ask yourself, well, what do the terms do as n goes to infinity? Because if they don't go to 0, the divergence test says that that series will diverge. Yeah, if they do go to 0, then you have to keep thinking. You have to try something else. If the series is super special, if it's a geometric series, then the geometric series test completely answers the question. Yeah, if the radius is less than 1 in absolute value, it converges, and you know its sum. If the radius is bigger than or equal to 1 in absolute value, it diverges. So a great test, it's a perfect answer, but it only applies to geometric series. The third one we looked at was the integral test. It applies to series whose terms are non-negative, decreasing to 0. It's a good test, but you have to be able to integrate the corresponding function. You have to be able to compute that improper integral. So if somebody hands me a series whose terms are the corresponding function, something I can't integrate, then I can't use the integral test. A special case of the integral test was things like 1 over n to the p. We prove, or you can use the p-series test. You don't have to recapitulate the integral every time. If p is bigger than 1, those things converge. If it's less than 1, they don't. All right, so we're going to add 2 more tests to this list today. So at the end of this lecture, we'll have 6 of them. Just so I don't have to keep writing it everywhere below, let me just say once and for all that in all of my examples below, the question I'm asking is, does the given series converge or diverge? All right, so if I don't write that over and over and over again, that's always my question. So let's take a look at this comparison test. Let me leave it at the bottom of the screen here so that example doesn't distract you. So it's a little bit of an intimidating looking test, the comparison test, because it involves not 1, but 2 series. Yeah, so there's a series a sub n and a series b sub n. I'm just going to say the terms a sub n and b sub n because my tongue trips up if I keep having to say the infinite sum as n goes from 1 to infinity of a sub n, the infinite sum of blah, blah, blah. You don't even want to hear it anymore either. So I'm just going to say the sum a sub n, the sum b sub n, or just a sub n's, b sub n's. Okay, and there's a catch that these series can't have negative terms. So the terms in them can't have any minus signs. So these are series with positive terms. And typically, you'll see as we're doing this, it doesn't have to be in this notation, but it's just sort of easier when we start. This series of a sub n is going to be the given thing, the one we're asking, does it converge or diverge? B sub n, you're going to come up with. You invent. But let's take a look at what the what this test says. It says that if you have these 2 series, a sub n and b sub n, and the terms of the b series are greater than or equal to the terms of the a series, well, then if the b series converges, then so will the a series. And it kind of makes sense because if term by term the b's are bigger, then their partial sums will bound the partial sums of a. So if those partial sums of b have a limit, the partial sums of a have to have one as well. All right. Conversely, if the b's diverge, the b's diverge, but they're less than or equal to the a's. Okay, so those partial sums of the b's are blowing up. Well, if the a's partial sums are bigger, the a series has to blow up as well. All right. So when you're using this test, you're going to kind of have to have a sense of what a sub n does. If you think that the series a sub n If you think this series A sub n converges, you're going to try to find a known to converge series that bounds it above. Yeah. If you think the series A sub n diverges, you're going to find a known to diverge series that bounds it below. So these are a little bit more sophisticated tests to use than anything in the list of 4 that we have so far, because you have to have a sense of what's going on so you invent the right series. Let's take a look. This first example, I've written it all out right now. In the subsequent examples in this lecture, I'll write them out as we go, but this one we can make kind of quick. Okay, so here is the given series. It's the series whose terms are 1 over n squared plus n plus 1. And the question is, does that converge or does it diverge? So here's kind of the main idea, and you're used to this when you're thinking about limits of polynomials. When n is very big and you have a polynomial expression, the leading term dominates it. The leading term of a polynomial dominates its size. So when n is very large, you can ignore that n and n plus 1 in the denominator. So this little wiggle equals here is just sort of approximately equal, or behaves like, you can almost read this. So for large n, 1 over n squared plus n plus 1 is basically like 1 over n squared, okay? 1 over n squared, yeah, so let me just say that ignoring the lower terms, 1 over n squared plus n plus 1 is like 1 over n squared. And then I have an inequality. 1 over n squared plus n plus 1 is less than 1 over n squared. Well, because n squared plus n plus 1 is definitely bigger than n squared, yeah? I'm adding something to n squared. It makes it bigger. Well, and fractions with bigger denominators are smaller. 1 over the sum of, as n goes from 1 to infinity, of 1 over n squared, that's a convergent p-series, yeah? Its p is equal to 2, which is bigger than 1. It's a convergent p-series. So we're in the situation where we've gotten the terms of our given series are greater or less than or equal to, sorry, the terms of our given series are less than or equal to the terms of a series that's known to converge. So part 1 of the comparison test says that our given series converges as well. All right, so that's kind of how we're going to use this comparison test. Let's try it on this one. Maybe you want to stop this video for a second and kind of think about this yourself. In particular, do you have some intuition of whether this series converges or diverges? What are its terms like? Let's try that for large n. For large n, 1 over 5 to the n plus 3, well, that's basically like 1 over 5 to the n, yeah? That plus 3 is not going to change that denominator very much when n is a super big number. 1 over 5 to the n would be the terms of a convergent p-series, or excuse me, convergent geometric series. Yeah, so if that thing converges, what I'm hoping is that its terms are greater than or equal to my given terms, and they certainly are, yeah? 5n plus 3 is certainly going to be, or 5 to the n plus 3 is certainly bigger than 5 to the n. In fact, it's 3 bigger. So when you reciprocate that, this fraction has a bigger denominator, so it's a smaller fraction. Okay? The series whose terms are 1 over 5 to the n is a convergent geometric series. Geometric series test says that thing converges. So since we have the right inequality, we are bounded above by a series who's known to converge. I should be saying all terms here are positive. Okay, so our series, the sum of 1 over 5 to the n plus 3, converges by the comparison test. Okay, so there's a second example. So just to run through it one more time, I've got to kind of do something to kind of give me an idea of how this thing behaves. And then once I know how it behaves, this thing is like a convergent geometric series. So I'm looking to bound it above by that convergent series terms. Okay, let's look at another example. This one I've got log n over n. It's not so clear what log n over n is like when n is large. Yeah, because there's nowhere to like cancel the n, there's no largest term, there's no numbers that I can ignore. N gets big, the logarithm gets big. However, you can say that, because the logarithm is getting big as n goes to infinity, it is true that this fraction, log n over n, is bigger than just 1 over n, because the logarithm will be bigger than 1. And bigger numerators make fractions bigger. Yeah. This thing is divergent. That's our harmonic series. I want you to know that name. The harmonic series, the series whose terms are 1 over the n, we use the integral test to prove that it diverges. The harmonic series diverges. Okay, well, look at this inequality. The series that we are considering is bounded below, term by term, by a series that's known to diverge. So the comparison test tells us that our series, log n over n, if you like, its partial sums are at least as big as a series whose partial sums are blowing up, this thing diverges by the comparison test. Cool. It's the third example. You'll notice it's not an accident. Let me show you this part. I just clipped this from your book, but I think it's good advice. When you're using this comparison test, yeah, you have to have a sense of what it's, you have to choose this B sub n, right? I said it above. You have to come up with this. And so you need to have some sense of whether your given series is going to converge or diverge to know which kind of inequalities you're looking for. But it's not an accident that I was just using P series, geometric series. They're often chosen to compare to these things because we know how those things behave. Yeah, if you can bound something above by a convergent P series, it converges. If you can bound it below by a divergent geometric series, diverges, and so on. So these are not just kind of random. P series and geometric series are sort of your usual suspects when you're looking for something to compare with. Okay, but I want to say that the inequalities can be difficult. Yeah, establishing the inequalities may be difficult, and sometimes they might even be worthless. You can end up, sort of finding out that your series behaves like something, but the inequality is kind of the wrong way. Let me show you what I mean with an example. So I've got this series down here, 1 over 2 to the n minus 1. Yeah. And 1 over 2 to the n minus 1 for large n should behave like 1 over 2 to the n. This thing is a, can you say it before me? It's a convergent geometric series. It's the terms of it, I mean. The terms of a convergent geometric series, 1 over 2 to the n. The ratio is 1/2. It's less than 1. But this time, we're not adding something to 2 to the n, we're subtracting it. So 2 to the n minus 1, whether you like it or not, you have to admit it's less than 2 to the n. It's not bigger than it. So the reciprocal, 1 over 2 to the n minus 1, has to be bigger than 1 over 2 to the n. Yeah. So I've got my series bounded below by something that's known to converge, but the inequality is the wrong way. If I'm if I'm greater than or equal to something that's known to converge, I might converge, I might diverge. So the inequality is pointing the wrong way. I don't have any way of concluding anything from that. So this inequality is worthless in terms of comparison. You need to be less than or equal to a known convergent series if you want to say something, or greater than or equal to a known divergent series. But this thing converges, so the inequality is backwards. All right, so it would be difficult to use the comparison test directly on this thing because, I mean, 1 over 2 to the n is kind of what we have to compare it to, but the inequality is backwards. The inequalities make the comparison test difficult to use in general. So that's where the second and final for this section result comes in, the limit comparison test. The limit comparison test is going to rescue us in example 4, because the limit comparison test basically lets you use the same kind of idea, but you don't have to worry about any inequalities. So let's take a look at what it says, and then we'll try to use it. So the limit comparison test, still have two series, and it's still going to be the case that one of them is kind of the given, and the second one you're going to invent. Yeah, so AN and BN, they still have to have positive terms. So no negative numbers here. But this time, we don't look for some inequality or anything like that. The ANs, the BNs, we don't care how big they are. We compute this limit. We take the ANs and we divide them by the BNs. And by the way, you can divide the other way. It doesn't matter. But let's just stick with what the book writes. So you can divide AN by BN and you take the limit. And if that limit exists, and well, there's a catch. That limit can't be 0, but it's not infinity. So if that limit exists, but it's not 0 and it's not infinity, then the limit comparison test says that both of your series converge or they both diverge, right? So they live and die together. If one of them converges, the other one does. If one of them diverges, the other one does. Cool. Let's look at example 4. You use the limit comparison test kind of starting the same way. It's still true that this 1 over 2 to the n minus 1 is very much like 1 over 2 to the n. Yeah. So if you want, these are my ANs, and so this is how I'm choosing my BN. My BN is going to be 1 over 2 to the n. So I'm going to take a look at the limit as n goes to infinity of my ANs divided by my BNs. Yeah, so I have to take that limit and simplifying that fraction a little bit. I didn't give myself very much room here. That's the limit as n goes to infinity of, well, what would it be? It would end up being 2 to the n over 2 to the n minus 1. And that minus 1 is not going to affect that denominator very much. So 2 to the n divided by 2 to the n minus 1 is going to have limit 1 as n goes to infinity. And 1 is not 0 and it's not infinite. So because, well, so the limit comparison test says that both of these series are given 1 and this one, n equals 1 to infinity, they either both converge or they both diverge. And since this one converges, do you know why? It's by the geometric series test. Then our original series converges. And that's by the LCT. Okay, so it's kind of the same idea as with the comparison test. You kind of choose this thing that behaves like it for large n, but unlike the comparison test, you don't have to worry about who's bigger or smaller or which converges or diverges. You just take a look at this limit. You certainly need to know, I mean, the BNs weren't chosen randomly, but yeah, you need to know if they converge. All right, so let's do one more example and then we'll call it a day for this, and you can ask me some questions about it in an online Zoom meeting. So here I've got the sum. It's too much to pronounce, really. You can see it, 2n squared plus 3n over the square root of 5 plus n to the 5th. All right, so what's that thing like? It's pretty busy looking. 2n squared plus 3n over the square root. So please drop in on a Zoom class and ask me if it's not clear about how I'm thinking about this. But basically what I do is I ignore lower order terms everywhere, lower power, I mean. So let me show you with color what I'm ignoring. I'm ignoring this 5 in the denominator because its exponent is 0, n to the 0. That's smaller than n to the 5th. If there were other terms down there, I'd ignore them too. The only thing that I'm not ignoring in that denominator is this thing, the highest power. Likewise, the highest power up here is the only thing I'm not going to ignore. This 3n for large n is not doing anything. So this thing is very much like, well, 2n squared over the square root of n to the 5th. And that is actually equal to 2n squared over n to the 5 halves. Yeah. And then by the rules of exponent, 2 is 4 halves. So this thing is equal to 2 over n to the 1 half, or 2 over the square root of n, if you like. So this is my comparer. That's going to be my bn. Yeah. And stop the video. Think about it. The series with those terms, do you know what it does? Yeah, I'm going to let it hang there for a second, but you should. One of our previous tests applies to a series with those terms. Good. Let's take a limit. We have to take the limit. This is going to look like a mess, but it's not going to be that bad. We have to take the limit of the an's over the bn's, okay? So that means I need to take my 2n squared plus 3n over the square root of 5 plus n to the 5th and divide it by those bn's. I'm a little lazy here. I'm going to multiply it by the reciprocal. I'm going to multiply it by the reciprocal, okay? And then let's just see algebraically what we get here. So this is the limit as n goes to infinity. If we distribute that n to the 1 half through the numerator, it would be 2 to the, well, n squared times n to the 1 half is n to the 5 halves. N to the first times n to the 1 half is n to the 3 halves. And down here in the denominator, I've got, I'm going to write it as 5 plus n to the 5th to the 1 half. So in this limit, we can ignore lower order terms, right? We don't have to pay attention to this 3 halves power. We don't have to pay attention to that 5. That 5 is under the square root. So this limit, by looking at the higher power terms, or if you want to be formal, use L'Hopital's rule, this limit is the same as 2 times n to the 5 halves divided by n to the 5 halves. Yeah, that's the square root of n to the 5th. And that limit, of course, is 2. Okay? So if that limit is equal to, oh, excuse me, I dropped this 2. Where did it go? Sorry about that. So I should have this, I should have that. It's 2 over 2, the limit is 1. Okay, wouldn't have affected my conclusion, but I should try to be accurate here. 1 is not 0 and it's not infinity. So since, have you answered the question? The series 2 over n to the 1 half, what does it do? Diverges by the p-series test. Then our series, the sum 2n squared plus 3n over the square root of 5 plus n to the 5th diverges by the limit comparison test. Okay, I'm going to stop it. I hope that wasn't too long. I hope those examples were illustrative. Do the activities, do all the homework in your book, and you will be proficient at this stuff.